Why we having some technical. Okay. There. Okay. So welcome everyone to this week seminar. We're going to have a talk given by Dr. Sylvia Tonen. She received her PhD from the Radboud University in Nijmegen, the Netherlands. She was also a postdoc fellow at Leiden Observatory and a Benny Fellow based on the Anton Pannekoek sorry, Institute in Amsterdam. And she's actually currently a professor at an assistant professor at this institute in Amsterdam. Her research interests include formation and evolution of binaries and triple gravitational wave sources, supernovae, and other stability of mass transfer and the interplay between stellar evolution and dynamics. So today she's going to talk about some binary systems and transient, and this talk, stellar interactions and transients, sorry. So Sylvia, you can start whenever you want.
Thank you.
We really thank you for accepting our invitation, and I'm really happy to see you.
I wanted to say thank you for the invitation to to show you a little bit about the work that we're trying to do here in Amsterdam. And yeah, indeed, the institute is called Anton Pannekoek Institute, which means Anton Pancake Institute, who was the founder of this institute. And that happened exactly 100 years ago. So this year we're going to try and celebrate that as much as we can. But about science, what I want to talk about today has to do with stars. So I'm interested in how stars evolve, how they interact with other stars, and how they every now and then can give rise to these bright transients that we can love and observe. And so let me try to go to the next slide. There we go. So the thing is that single stellar evolution is something that astronomy has been investigating for centuries now, right? And it's something that even if stars are not the thing that you're investigating directly, they're still very important because they're the fundamental building blocks of our galaxies and of our clusters and the solar neighborhood, or as hosts as exoplanets. But we've also known for many decades already that many of the stars are not single stars. So the majority of stars actually have stellar companions. And these binaries, they are very abundant, and it matters because it completely changes the evolution of a star. So the evolution is different, and it can give rise to these stars that cannot be formed in any other way, like helium white dwarfs, or like massive black holes, stellar mass black holes, or even blue stragglers. It also matters because these stars, they affect their surroundings in different ways than single stars would do that. So through chemical feedback, radiative feedback, mechanical feedback. And here you see a really nice example of the flux that comes from a stellar population that can ionize the material around it. And so in red, you see what we expect from a stellar population that only has single stars. And then in blue and orange, you see what is added, what extra ionizing flux we get if we take into account these binaries and these binary interactions. Now, I think binaries are also very interesting for transients because some of these transients are even just caused by the fact that these stars are in binaries, like the stellar mergers or even gravitational waves, right? When we have compact objects that merge with one another. And then there's also the supernovae that they can also come from single stars. But if a star is in a binary system and it's infected or affected by these binary interactions, it can completely change the way that the supernova looks like. So it's all of these different aspects where, it matters that these stars are in binaries. Now, I always want to say that I'm super, super excited for this field because I really feel like there's a revolution on the way. There's this overwhelming amount of data coming our way that sometimes makes me feel a little bit like Simba in The Lion King. I don't know how many of us can still remember The Lion King, but it definitely makes me feel like this sometimes. And every now and then it makes me feel like this because there's that much data coming. And then I'm talking about data for stellar sources. So for example, from Gaia or from SDSS-5, from the Vera Rubin Observatory, but also the transients that these binaries can give rise to. So those are electromagnetic transients that we're observing with ZTF and future Vera Rubin Observatory, Black Gem, but also gravitational wave transients, right? That we can see with LIGO and the future LISA and the Einstein telescope and all these things that are coming our way. And just to give you a little bit of a feeling of how much of a revolution I'm talking about. So if we focus on supernovae, we currently observe something like 3 supernovae per night. So that is with ZTF, with this Wiki transient facility. And I think 3 supernovae per night is already quite a lot, right? Like that is adding up if you do that, you know, for a year, right? I'm still used to working with samples that had 10 objects or maybe 25, and that was amazing. So imagine what 3 per night is doing. But in just a few years, when the Vera Rubin Observatory comes online, this is going to go up to 1,000 supernovae per night, right? So we're going from 3 to 1,000. That's 2.5 orders of magnitude increase that is coming our way. So that is really a gigantic increase. Now, it means that we can study these populations in a lot more detail, right? We'll understand the characteristics of that population much better. And it also means that, you know, some of the sources that may sound very rare and obscure right now, they're definitely not rare and obscure anymore in just a few years. So there's a need for us to understand these, you know, more special systems as well. And I actually would turn it the other way around, saying that theory, because I'm a theoretician, so I can provide criticism to myself, saying that we also need to make changes because some of the simplifications that we've been doing so far, they are not going to be valid anymore for these huge populations, right? We also need to start doing things in more detail when the observations provide that detail. So I want to give you a couple of examples for that today. So the first one I'm going to talk about is stellar mergers. Then I'm going to talk a little bit about triples because stars are in binaries, but they're also very often in triples. And then I'll talk a little bit about transients that come from all of these objects. So let's start with these stellar mergers. Yeah, so I think these are very interesting sources. These transients from, we think that these stellar mergers can give rise to bright transients that are a little bit in between novae and supernovae in brightness. And we have about a dozen of them at the moment. We have observed about a dozen. So how do we know that these events are actually stellar mergers? Well, that's really cool because this first object, V1309 SCO, the transient was observed, and then Tilenda and collaborators, they went to archival data. And at the same location in the sky, they found that there used to be a binary there, and that the orbit of that binary was slowly shrinking over time until the moment that this transient occurred. So that's such a nice and beautiful example of that these mergers indeed happen and can give rise to these transients. Now, and we call these transients luminous red novae or intermediate luminosity optical transients. It's a long name. Now, based on these transients and also based on merger remnants of these stellar mergers, we roughly have an estimate for their rate, and that's something like 1 event every 10 years in the Milky Way. Right? 1 event every 10 years is pretty often. And it means that there are lots of stars out there that are not just normal single stars, but that actually are these remnants of these mergers, right? So I call them stars that have a flaw in them. Now, why do I call it flaw? Because, you know, a remnant, a merger remnant, may be very different than a single star. It may be rotating rapidly. It may have developed a magnetic field. It may have a very weird size of the core relative to the envelope. And the difficulty is that all of those characteristics that I was just naming are indicators that a star is a merger remnant, but all of those might not persist for long times. And the ones that we can detect with astroseismology, so this weird ratio between the core and the envelope, so we could detect that, but that's also quite expensive to do, time-wise. And so with all of these merger remnants hiding in their stellar populations, I think that's something interesting to take into account in galactic archaeology. So let me explain to you why I think these systems are so interesting there. And for that, I want to have a look at this white dwarf population, this sample that we have of all the white dwarfs within 20 parsec. And this is a really special sample because it is nearly complete. It has a completeness level of 95 to 99%, but that's really ridiculously high. Now, why am I so interested in these white dwarfs? Well, I know many of you are working on white dwarfs, so I probably don't have to tell you that white dwarfs are interesting. But one of the reasons why they're so interesting is because we can use them to measure stellar ages, right? If you measure the mass of a white dwarf and you assume it was always a single star, we have a pretty good idea of how long, like which star this used to be and how long that star took in order to become a white dwarf. And then if you measure the temperature of the white dwarf, we can get a pretty good idea for how long this white dwarf has been cooling. So if we add these two, we get a rough and a pretty good idea for the age of that white dwarf. Now, that was done by Pierre-Emmanuel Tremblay in 2014. He measured the ages of the white dwarfs exactly in that 20 parsec sample. And here you see a histogram of all of the ages that he measured. And what it represents in the end is a star formation history of the solar neighborhood. And so the reason why I think mergers are interesting here is, well, what if some of these objects here were actually merger remnants? Then their age could actually have been much older than what we would estimate. So for example, a 2 solar mass star becomes a white dwarf in about 1.5 gigayears. But if we take a 1 solar mass star that merges with another 1 solar mass star after the main sequence, it would pretty much give the same white dwarf mass, but it would take about 12.5 gigayears to get there, because it takes 12.5 gigayears to come to the end of the main sequence. So there's a potential here to be wrong by gigayears. Now, in order to see how common these mergers are, we had a detailed look at that 20 parsec sample. And so what you see here is the 20 parsec sample, and in blue, you see that 78% of the white dwarfs in this sample are single. And then in the other colors, you see other types. So those are the binaries, and we have double white dwarfs, we have white dwarf main sequence systems, we have compact systems, resolved systems. That's the 4 different colors. Now, and the one thing that strikes me in the sample, and I'm not the only one that, I'm not the first one to notice this, is that the binarity fraction is quite low, right? We only have about 25% binaries in the sample. That's interesting because if you think about the main sequence stars that these white dwarfs came from, then their binarity fraction is roughly 40 to 50%. So where have all of these binaries gone, right? How have we gone from 50% to 25%? So this has been called the missing white dwarf binary problem. And you can probably already guess in which direction I'm going to explain this. But what we did is we modeled the evolution of stars and binaries in the solar neighborhood, made different assumptions for the initial orbits that they're in, the star formation history. We took into account the selection effects that, of course, play an important role, right? Because a very dim white dwarf is very hard to find next to a bright giant. And then we try to see what will we expect from theoretical grounds for this 20 parsec sample. Now, what we found is the following. The ranges here represent the ranges that we find in the different models. And roughly, if you look at this, then there's a couple of things that I want to notice. One is that the overall total number of systems is very well reproduced by the theoretical models. So the total number of systems fits within a factor 1.5. So the theory is doing really a good job in order to predict these space densities for these systems. The other thing that you might notice is, well, and that's the case for the blue systems, but also for the red, for the yellow, for the purple. The other thing you might notice is that there's all of a sudden an extra color, right? Those are the stellar mergers. So observationally, we just know if a star, if a white dwarf is single or not. But theoretically, I can have a look at the stars that really live their lives as single stars always, that's in blue. And this lighter color, those are the ones that come from stellar mergers. And what it shows is that 10 to 30% of the white dwarfs actually come from mergers. So 10 to 30% is a very large number. Now, before I continue on these mergers, I have one quick detour, and that's these green systems. Because these green systems, you see that I'm over predicting them. Now, what are they? They are double white dwarfs in very wide orbits. So no binary interaction, no mass transfer. My computer went to a couple of next slides. So it's very curious why we're over predicting only this one population by about a factor 10. So the thing that we were speculating is maybe these wide binaries we can disrupt by their own stellar winds. And something similar was observed later on in the Gaia data by Al-Badri and Walter Ricks. And they speculated if white dwarfs maybe actually could get kicks that dissolve these binaries. So that's an interesting puzzle. Okay, I'll quickly continue. So if we have a look at these white dwarfs that come from mergers in the simulation, where do they come from? Now, this plot is showing which fraction is coming from which type. So if it's a double white dwarf merger, a giant plus main sequence, or double main sequence, in red you see our default model, and then the other colors represent the other models that we made. You know, if you have questions about this, I can, tell you more about the models later. But for now, just look at it as a bit of the uncertainty on the predictions. And what you see is that about 10 to 20% of all of the mergers come from double white dwarfs, but they also often come from giants that merge with their companion or double main sequence stars. There's a variety in mergers that give rise to single white dwarfs. And I highlight, of course, Karel Temmink, because he's the student that did this work. Now, the other question is, so if you use a white dwarf to measure the age, and accidentally this white dwarf turns out to be a remnant of a merger, how wrong would you be in your age estimate? So that is what this graph is showing. That's the delta t, so the difference in age as a function of white dwarf mass. And you can see that sometimes the age difference goes up to like several gigayears, like the example we saw before. But of course, the majority is smaller than that. On average, the formation of a binary takes about 1.5 to 5 times longer to get a white dwarf compared to single stars. And on a population, the average age would be underestimated by about 50 to 500 megayears. So that is similar to the current error on white dwarf ages. So if our instruments are improving, then these merger remnants definitely would be something that we cannot ignore longer. Now, another thing to mention is that for massive white dwarfs, the merger fraction is even higher. 30 to 50% we expect to come from massive stars. And the last thing is that I think the future is really bright here, because with Gaia, that 20 parsec sample can be expanded. It can be, we can come up with a sample that is complete out until 50 parsec, maybe even as far as 100 parsec. which means that this sample is going to at least increase by a factor 50. So that's great. So we can study these systems in more detail, and we can also test the binary models in more detail. So I want to make a transition and give you an example of another thing that I think we should start looking at in more detail, and that is triples. Now, why triples? Well, I think they are more abundant than people often give them credit for. So how abundant they are is shown in this diagram here. So you see, for example, if we focus on solar mass stars, then we have pretty good measurements of the binarity fraction and the triple fraction. And you see that in green, there's about 30% binaries and 10% triples. So for every 3 binaries, there is 1 triple. You know, that's not a very low ratio, right? Still 10% of triples, but 1 in 3, it's not negligible. Now, if we go to more massive stars, we see that they are very rarely found as single stars. They're actually very rarely found as binary stars, and they're predominantly found in triples and quadruples. So as we go to more massive stars, triples are not a minority, they're actually the majority. They are the ones that that dominate the population. Now, when I talk about triples, I talk about systems that look like this. So this is where we have 2 stars in an orbit around one another, and a third star in a much wider orbit going around the center of mass of that inner binary. So it's like we have, well, so we can approximate this triple by 2 Keplerian orbits that interact with one another. So you're going to hear me talk about the inner orbit and the outer orbit, the inner eccentricity and the outer eccentricity, these types of things. And these systems, they can be stable for long times, and that also really helps to make them so abundant. Now, if we really want to understand their evolution, it turns out that we need 3 ingredients. So the first one of that is 3-body dynamics. And maybe some of you have studied the 3-body problem in their undergraduate course, and you may remember that we don't have a general solution for the 3-body problem. Instead, what we have is approximations that are valid in parts of parameter space. And I really want to give a lot of credit to this field because there's been a lot of progress to understand all the peculiarities of 3-body dynamics. And so we understand this better and better. It's really huge progress. Most of these studies so far, they have assumed that the stars are point particles, which completely makes sense, right? That's where I was going to start as well, if I would work on that field. But you can also imagine that at some point, it's not that good of an assumption anymore to assume that your star is a point particle, because stars evolve, right? Their radii grow, they lose mass in their winds. And also because there is dissipation. There is tides, there's gravitational wave emission, and they drain energy and angular momentum from the system. So most of the studies so far focused on 3-body dynamics and ignored these other 2 processes, or vice versa. And only the handful of objects or the handful of projects that look at this combination, they have shown that it's a really rich regime that opens up a lot of new interesting channels. And so in order to understand better how these triples evolve differently from binaries, I developed a code to simulate the evolution of triples consistently, to take those 3 ingredients into account simultaneously. And the code is called TRAS. And of course, I want to highlight all of the members of the TRAS team, because all of the results that I'm going to show you later on, they are because of the entire TRAS team. Now, before I go to those results, I have just a few more slides to give you a bit of an intuitive feeling about 3-body dynamics. So as I said before, we approximate these systems by 2 orbits that interact with one another, 2 orbits that perturb each other, that torque one another. Now, in reality, that means that I'm solving a set of differential equations, and I can either take you through every term of these equations, but that's pretty awful, So instead, I brought a tool. It's a very highly technologically advanced tool that I'm going to show you. So Alejandra, if you're not seeing me, then please say something. So otherwise, I'm going to introduce you to the tool. The tool looks like this. This is the inner binary. And then this is the outer binary. Of course, this is completely not to scale, but otherwise I couldn't hold it in my hands. And of course, these are perfect ellipses, you know, bear with me. So what is going to happen with these three-body dynamics is that we're going to have Kozai-Lidov cycles. In those cycles, it's the inclination of the inner binary that goes up and down and up and down, right? So we get these cycles here. At the same time as that the inclination changes, also the eccentricity changes, just to conserve angular momentum. So we become more eccentric, more circular, more eccentric, more circular, more eccentric, more circular. So that's pretty much the basics of the three-body dynamics. And I'll just go back to sharing my screen again. Yeah, we share that screen. We go full screen. Yeah, and again, if you're not seeing my slides, full screen, Alejandra, just give a yell. But to quantify these Kozai-Lidov cycles in a bit more scientific way, I've also shown you this example here. Here you see the eccentricity and the inclination as a function of time, and you see these huge cycles, right? We get eccentricities that can go as high as even close to 1. Now, why do I care so much about this high eccentricity? Well, because at high eccentricity, the stars come close to each other, and that's when they can interact. So let me give you an example. This is again a binary, and we're going to put a third star around it later on. So what you see in the diagram is the orbital separation as a function of time. So in the case of the binary, pretty much nothing happens to it. It's a wide binary, it just becomes a little bit wider as these systems are losing a little bit of mass in their stellar winds. Now, if I put a triple around it, you see this. Very, very different. Now, why is this path so different? If we zoom in on that point, we see those huge eccentricity cycles. And at some point, the eccentricity becomes so large that one of the stars fills that rush slope and we get a phase of mass transfer. In this case, it's unstable mass transfer. The orbit shrinks very rapidly. And then the system keeps on continuing to evolve. We get another phase of mass transfer a little bit later and eventually a merger of two stars. Now, this is interesting because this is a merger of two massive carbon-oxygen white dwarfs. So it means that I can take a binary that doesn't do much and turn it into a merger of two carbon-oxygen white dwarfs, turn it into a supernova type 1a progenitor, just by taking into account that there was a third star, right? So we go from nothing to a supernova just by taking into account that third star. Now, I also want to mention that this is just one example, right? Just one system. And I can always come up with one system that does something interesting. So the question is, how often does this really happen in a full population? Now, with that in mind, I did a full population synthesis study of triples, made different assumptions for their orbital configurations at the start of the simulation. And here what I want to show you is how these triples evolve typically. So in blue, you see that that's the largest part. And the majority of these triples, they will get mass transfer or will experience at some point mass transfer in that inner binary. That's about 64 to 75%. It's a nice number, but it means more if you compare it to binaries, if you compare it to what binaries are doing in that mass range. Now with binaries, it's about 1/3 of systems that experience mass transfer. And so what it means is that triples interact more often than binaries by a factor 2 to 3. So at this point, I want to take one step back and put two things together. And so if there's only one slide of this colloquium that you're going to remember, let it be this one. So what I want to show here is that I used to think about triples as something that, occurs, but not that often. And actually what I tried to show in the beginning is that, well, 1 in 3 binaries, or for every 3 binaries, there's 1 triple at least, right? Sometimes it's even more than that. So, we kind of equalize that scale a little bit. Now, the next thing I'm telling you is that, hey, but these triples, they interact more often than these binaries. So if you're interested in something that you need an interacting binary for, then the scale actually equalizes even more. So it puts these triples almost on even footing with the binaries. And I think that's a very interesting aspect. Okay. I'm going to go to this slide. And I quickly want to show you these other parts of the pie chart. So in yellow, you see systems where it's the secondary that starts a phase of mass transfer when the primary is already a compact object. So what I get is a white dwarf that's accreting from a companion star without ever having to go through any previous phase of mass transfer. And the people working on CVs, for example, they know that there's many complications in that common envelope phase that happens before. So I'll come back to that later on. The green systems, those are systems where you have a tertiary star that's donating mass to an inner binary. That's also really interesting. And in those cases, if a circumbinary disk can form, we expect that most of the accretion would happen on the lowest mass object until these masses equalize. And then the accretion could happen to both stars. And so one of the predictions that you would expect from this is that you end up with binaries that have very equal masses. So interestingly enough, we see such a system where both of the stars are very equal in mass, plus we know they have accreted. So this is a double blue straggler. Now we've also tried to estimate how often this happens for other types of binaries where the inner binary has already evolved to have some compact objects. And we roughly estimate this to be about 5 to 10% of 5 to 10% of double white dwarfs to experience such a phase of mass transfer. There's some more colors in this pie chart. We have the purple systems. Those are systems where there's no interaction. So the stars pretty much just live their lives as single stars. And interestingly enough, we actually found such a system. So in the second data release of Gaia, we found a triple that consists of 3 white dwarfs, and they're all in white orbits. So it means that a triple can indeed survive for these long times, and a triple can survive all of these mass loss phases. And it's just really nice to have this observational confirmation of it. Now there's also I'll come to that later. But right now, I want to make this transition to the last part of my talk. And the last part of my talk has to do with transients. Now, when I reached this part of the talk, I was feeling a little bit like this. Like, I've been trying to paint this beautiful picture of triple evolution and how elegantly the three-body dynamics affects the binary. But I don't know about you, but when I build a sandcastle on the beach, one of the parts that I enjoy the most is just in destroying it afterwards. So that's what I'm going to do. I'm going to start with that triple, and we're going to destroy them. And the way to destroy them is by having the binary or having the triple make a transition to, I clicked one time too often, to another dynamical regime. So we start with these triples on the left, and we make the effect of the tertiary stronger, such that we get a reaction like something on the right. And these are interactions that we typically think of in the context of clusters, right? So here we have a binary and we shoot a third star at it. And you can see that these systems can experience very close passages, that we can have exchanges between the stars. And every now and then, when the stars get close enough to each other, we can even get a collision between two of the stars. Now, that is something that we looked into very recently. And we found that collisions indeed happen in about 10 to 25% of these triples that become unstable. That was the red part in our diagram. They just become unstable from their own internal evolution, just from the fact that they lose mass in their wings. And it happens at about a rate of one event every 10,000 years. I'd love to talk about this more, but I want to make sure that I have enough time for one other scenario. So let me go to that scenario. And that is bringing me, let's see, how much time do I have? Until like 20 past, right?
Around 10 minutes.
Around 10 minutes. Okay. Okay, then I'll quickly go past these. So I was talking about these red systems that become dynamically unstable. We can also do that when we have compact objects in the triple. So here I'm just thinking about a triple where the stars evolve, they become compact objects, and then they make that change into this dynamical regime that is more heavy, that is more extreme. That's from their own stellar winds or maybe from the supernova kicks. Now, if we do that for white dwarfs, we can go into the situation where the inner binary gets such a strong eccentricity that we get a collision between two white dwarfs. That's interesting because collisions between white dwarfs can give rise to supernova type 1a. And supernova type 1a are a type of transients that I worked on a lot in the past that I find very interesting. But one of the problems is that we don't know what their progenitors are, even though we can use them so efficiently to measure distances in the universe. We don't know what their origins are. Now, so we try to model the evolution of these triples, try to see how often white dwarfs collide, but unfortunately, we find a rate that is about at least a factor 100 to 1,000 lower than the supernova type 1a rate. So unfortunately, I think this simple channel, this particular channel is not going to solve the type 1a progenitor issue. But we can do something similar with black holes, right? Here we don't need a collision between black holes, just a merger is good enough in order to get a gravitational wave. And the rates that we estimate for this give rise to several percent, like several tenths of percent of the observed LIGO rate. So that means that these triples can already give rise to a good fraction of all of the sources that LIGO is observing right now. And the one thing to stress here is that most of the massive stars are in triples, right? The massive stars are the ones that form the black holes that we need for these gravitational wave sources. And they're not sometimes in triples, they're most of the time in triples. And this channel I'm presenting here is only one. And we're really only standing at the beginning of investigating all of these other triple channels in which these massive stars can give rise to gravitational wave sources. I'm not going to talk more about that today, maybe another time, because I want to save a few minutes to talk about cataclysmic variables, because we just submitted a paper linking triples and cataclysmic variables together. Now, I know many of you are probably working on this, but for the few that are not, cataclysmic variables are binaries in which we have a white dwarf that's accreting from a companion star, just a regular regular star that's burning hydrogen and helium. The amazing thing, the thing that I find amazing about these systems is that we have a pretty good understanding of how they evolve. Like there's a basic evolutionary scenario that's accepted. And in that scenario, as you can see here, we start with a donor star. I lost my mouse. We start with a donor star. And as that star is donating mass and reducing its mass, we know that the period is slowly going down and down until this moment that it reaches the period minimum, and then we expect the systems to turn around. Now, our basic model is reproducing these observations quite well to first order, But to second order, there's also lots of problems that we still have in the formation of these sources. So for example, that the white dwarfs are very massive in these CVs, and that doesn't match with what we would expect from theory. So what happens with all the low mass white dwarfs in these CVs? Another thing is how many sources. So from theory, you would expect lots of sources to be here past that period minimum, but observationally, we only found a few. Another aspect is the temperatures of these white dwarfs and their mass transfer rates. So that's what I'm showing in this diagram here. Again, you see, how they would evolve. So there's periods slowly going down. And that period translates to a specific mass transfer rate. And given the mass transfer rate, you expect a certain temperature for the white dwarf. Now, if these white dwarfs temperatures are measured, then we see that they're, a bit higher than what we would expect from theory. But there's also a few sources that are really clear outliers. And one of them is T-Pix. T-Pix is a cataclysmic variable that has gone in outbursts many times. Actually goes in outbursts every 30 years. It's maybe one of the best studied cataclysmic variables. But it has a very high luminosity, a very high temperature, a very high mass transfer rate, a mass transfer rate that is 1 to 2 orders of magnitude higher than what we would expect. So what has been proposed is that, well, maybe in this system, the white dwarf is so warm it's irradiating the main sequence star, that's puffing up and therefore giving a higher mass transfer rate. Now the question, that's a really nice model, and it could explain lots of things. But the question is, it's a bit like the chicken and the egg, right? So you need the irradiation to puff up the main sequence star, but why did this white dwarf start to irradiate the main sequence star in the first place? And if this is very common, why don't we see it in so many other sources? Now, interestingly enough, recently we found a third object around T-Pix. So that is, interesting, because it makes you wonder, is there maybe something that triples can do to kickstart this cycle, So very quickly, normally for the formation of cataclysmic variables, we expect something like this. So we expect it to happen in binaries. We start with 2 main sequence stars. And then at some point, these stars interact. There's a mass transfer phase. They join one common envelope. And in that common envelope, the orbit shrinks a lot. And we form one white dwarf. Now, in that very compact orbit, in that very compact system, this is when the main sequence star can start transferring mass to the white dwarf, and we can get that cataclysmic variable. Now in triples, there's 3 different ways in which I can envision that we can make a cataclysmic variable. And these are 3 systems, 3 things that you've already seen before from that pie chart that I've shown. So in the first case, it's that orange group, right? These are systems where one of the stars just evolves by itself, becomes a white dwarf. Fine, it's a white binary. And then the 3-body dynamics kicks in because of that mass loss. The inner orbit shrinks, and the secondary star starts transferring mass to the white dwarf. The second scenario is very similar, but the 3-body dynamics are just a little bit stronger. That's the red systems, and this triple becomes dynamically unstable. And in those unstable interactions, we've seen that we can get collisions between the stars. Now, if tides are a little bit more active, then I could also give rise to a compact binary. Now, the third channel that we looked into is very similar to the ones in binaries. This is where the inner binary experiences a common envelope, pretty similar to what I showed on top. Now, the cool thing here is that from the mass loss of that common envelope phase, that's actually enough mass loss so that you could unbind the tertiary star. So in all of these scenarios, you expect that third star to be at very large separations, which is exactly where we see that third star with T-Pix. I forgot to mention, but it's at several 10 to the 6 solar radii away. So that matches actually quite well with what we expect theoretically. Now, when we look at the birth rates that we would expect from these channels, then the birth rate from the binaries is always a little bit high compared to what we see observationally. But if you compare it to what we expect from triples, then you see that this is actually quite comparable, right? So definitely showing that triples can contribute a significant amount of cataclysmic variables and making it reasonable that T-peaks could be formed in this way. Now, the other interesting aspect is that in these scenarios, that in a binary, when it starts donating mass to that white dwarf, the inner orbit can still be significantly eccentric. This is something that you do not expect in binaries, but something that can happen in triples because we have those Koda-Leibov cycles that pump up the eccentricity. Now, at these high eccentricities, the mass transfer develops in very different ways. It's not steady over the entire orbit, but instead we only have some mass loss every time that the stars pass by their pericenter. So you have pulse mass transfer, a little bit of mass transfer, nonetheless. And when this star like plunges into that pericenter, it can have a mass transfer rate that's much higher than what you would expect from binary evolution. So we propose here that through this eccentric mass transfer, that could be a mechanism to actually kickstart that cycle of irradiation-induced mass transfer. So that is the last part of what I wanted to show you today. So I'll quickly go through the summary. And what I wanted to show you today is that I think the future is really bright because we're getting all of these more observations. The samples are increasing by incredible amounts, 2 to 3 orders of magnitude sometimes. And that means that we can go make the next step. We can go to that next level. And at that point, I think triples are becoming very interesting because they are not rare. They're actually very common. I've tried to show you that mergers are very interesting as well, that mergers are common as well, and that they are important for estimating stellar ages, right? If we want to do galactic archaeology in a lot of detail that we can do with these large samples, we should start thinking about how stellar mergers change the measurements. Now, I also talked a little bit more about triples, try to show you that we now have a code that we can use to simulate the evolution of these systems in a consistent way, try to show lots of new evolutionary channels that they can give rise to, and even try to show that they are very important for gravitational wave sources, but also for the lower mass sources, even for the cataclysmic variables. And the last thing that I want to show is if you're interested in triples, then check out our Facebook group. We also have a web interface. If you have observed a triple or you have an object that might have a third companion, you're trying to see, is this possible? How strong are the dynamics? You can just plug it into our web interface. Both links you can also find on my own website. And the very last thing I want to mention is that I have a PhD and a postdoc position available to look into triples. So if you're interested in that, then feel free to drop me an email. And with that, I'm going to say thank you. And if you have any questions, feel free to fire them at me.
Thank you very much, Sylvia. Very, very interesting, very didactic talk. And now we can go out. Sorry, for the people that is following us in YouTube, we're going to stop our transmission, and we are welcome you next week for our next seminar.